Dear students, welcome to this paper which is Organic Chemistry 4. That is, in this paper we will be studying about advanced organic synthesis, supramolecular chemistry and carbocyclic rings. To begin with, we will be starting with the disconnection approach, and in this particular module we will be looking at the fundamentals of the disconnection approach, where you will be acquainted with how the transformations in retrosynthesis take place and what are the important terms that you have to be aware in retrosynthesis. You will be able to know about the basics of disconnection approach, or which is also called as retrosynthetic analysis. You will be able to understand what is the requirement for the disconnection approach in organic chemistry and what are the ways or the routine in general for designing the synthesis through this approach. So, let us begin understanding all this new concept about the retrosynthesis. Dear students, organic compounds are diverse in nature and their application, as you are already aware. These organic compounds, which are millions of them, have utilities in all walks of life, including food, pharmaceuticals, cosmetics, polymers, detergents, etc., to name just a few. Actually, as you know, everything around us and inside us is chemistry. One of the major tasks of the organic chemist is that how to deal with the synthesis of these compounds. Disconnection approach is actually a helping tool for the design of their synthesis in the lab, and this is known as retrosynthetic analysis. Actually, if you look at the term retro, it is the reverse. This means it is the reverse method of observing a molecule, keeping their synthesis in mind. This is a synthetic route to the target molecule from the simpler molecules or simpler starting materials. Till now, you have learnt about the reactions that this plus this will be giving you this particular molecule. So, what is retrosynthetic? It is actually looking at the product and thinking what molecules you can join through which route to get that particular product. So, this is actually a synthetic route to the target molecule from the simpler molecules or substances or the substrate that you can visualize and imagine and then compare. So, this approach of disconnection to synthesis is now a basic part of every organic synthesis course. So, you can say that if there is a target molecule, you have to now visualize that from where we do the disconnection, so that we get simpler molecules, and then how to connect and get this parent or the target molecule. If we talk about history in this field, Professor Elias J. Corey of Harvard University won the Nobel Prize for introducing the concept of retrosynthetic analysis in 1990. According to him, retrosynthetic or antithetic analysis is a problem solving technique to convert the structure of a synthetic target, which is called as the TGT molecule, to a series of gradually simpler structures via a path which finally indicates to simple or commercially available starting materials for a chemical synthesis. The main goal of a retrosynthetic analysis should be to reduce the molecule to similarly sized building blocks of lower or similar complexity. The process of simplification should be continued until you reach the molecules which are commercially available. So, this is very important that you have to keep in mind. And now you can see here that these are the various big molecules which can be the target molecules, because they are so commonly used by the mankind that organic scientists, they always try to look up that how we can have a simpler route which is economically more viable, commercially more viable, so that these can be prepared in mass scale to meet the requirement of day by day increasing population. You can look here, this is diazepam, which is a tranquilizer. Then this is the vitamin B12, which is riboflavin. Then we have abscisic acid, which is a natural hormone in plants, and you can see this is caffeine, which is a stimulant. We have beta carotene, which is a natural product with high nutritional value, but now we need to prepare this in synthetic large scale. So, how to break this, disconnect it to make it from simpler molecules is what all we will be studying about. Another example you can look is DDT, which is banned, but then initially even this various disconnection routes were adopted, so that this molecule could be made in a commercial scale. So, these were the chemical structures and some of the applications of a few molecules, but you know organic chemistry is full up of millions of these molecules, and many of them have now various applications in our day to day life. So, the design of the synthetic route requires the help of disconnection approach, and this topic has been incorporated in the syllabus to make the students aware about the synthetic methodologies of simple and complex organic molecules. So, starting from this module and the subsequent modules, we will be talking about how different ways you can look up in making this approach possible in lab, and then we will be taking many examples which will be learning for you, and then you can design your own disconnection approach for any target molecule, that how you can synthesize it through various alternative routes and then take that particular route which is more commercially viable. So, let us now go ahead and try to know what we mean by transformations in retrosynthesis. The various ways of transformation which are useful in retrosynthetic analysis, we will study them one by one. First, we will look at the functional group interconversion. Many functional groups can be interconverted into each other. For example, oxidation of an alcohol can easily give rise to an aldehyde, which further on oxidation can give rise to carboxylic acid, and this you have studied in your previous classes. Many organic transformations can be used for carrying out these functional group interconversions. Another functional group is carbonyl groups, that is aldehydes or ketones, which are also very much useful in this particular respect, as you can see in this particular figure, where this aldehydic group can be further oxidized or reduced and so on, and all the reaction that you have studied in these particular functional groups, you have to recall them and now try to apply. The reactivity of the carbonyl group can be masked also during the synthesis as a double bond. For example, ozonolysis can be used for the functional group interconversion into aldehyde, that is from alkenes you can prepare these aldehydes by cleaving this double bond, or dioxylane until it is needed. So, all these reactions that you have studied earlier, now you have to, and using your analytical mind, just apply that how you can build up these target molecules. Let us talk about another approach, which is functional group addition. Retrosynthesis gives a more functionalized compound. The rationale of using functional group addition approach could be that the specific function is easier to make, or that the specific function enables installation of another functional group. For example, as you can see here, that the cyclohexanone is converted into cyclohex-2-enone using the functional group addition approach. Here we can see that the single functional group in cyclohexanone is the carbonyl group, which gets converted by the functional group addition to two functional groups, that is one is the ketone and another is the double bond at the conjugated position. There is an additional functional group, that is the alkene, which has been added. So, we call this as the functional group addition approach. As you can see here in this figure, it shows another example of functional group addition, and here what you can see that the hydroxyl functional group has been added to the existing chloro functional group. So, initially you start with this chloroalkane, and by the functional group addition at this terminal CH3, it is getting converted into CH2OH, that is one more functional group is being added. Yet another way of carrying out transformation in retrosynthesis is the functional group removal. This transformation involves the removal of a particular functional group during the retrosynthesis, and as you can see in this particular figure, the alcoholic functional group is removed from the 6-hydroxy cyclohex-2-enone to give us cyclohexanone. So, the earlier example where we talked about addition of functional group, now we are talking about the removal of the functional group. Another example you can see here, here also there is a removal of functional group which is hydroxyl group, that is starting from this chlorohydroxy compound, you are getting chloroalkane and there is a removal of OH functional group in both of these examples. Another approach towards disconnection methodology will be functional group transposition, and this particular transformation involves the interchange of a functional group during retrosynthesis. For example, isomerization can be another term for the description of functional group transposition. This means the functional group are not changing, but you are getting the change in position or the isomerization which is happening. For example, you can look up this particular case, the double bond to start up is in conjugation with the carbonyl, but via the functional group transposition, the double bond has now shifted from this position to the non-conjugated position. So, after knowing these 4 broad ways of retrosynthesis, let us become familiar with some important terms in retrosynthesis that we will be very commonly using. The first term that you should be familiar with in retrosynthesis is the disconnection. In retrosynthesis, what we mean by disconnection is the reversal of a bond forming reaction, and how it is done? It is the cleavage of a bond to break the target molecule into possible starting molecules is called as the disconnection. That is, you are not connecting, but you are disconnecting, and that is what is the disconnection term coming from. The crucial steps in many syntheses is or are the bond formation. The reverse bond disconnection, while in planning a synthesis, helps to identify suitable synthetic routes, and there is no general way to disconnect a molecule, but we will be dealing with various examples, and that is how you will be able to know how to deal with the various disconnections. The next term that you have to be familiar with is the synthon. An idealized, often charged molecular fragment is known as synthon. Functionalized nucleophile can be denoted by DN synthon, where D represents the donor and N denotes the distance between the functional group and the reactive center. Functionalized electrophile is expressed as AN synthon, where A is the acceptor. Every retrosynthetic problem requires its individual creative solution. Experience and training are necessary traits for retrosynthetic analysis and planning of synthesis. The wider the span of knowledge of reactions and their scope someone knows, there will be more options that you can look up for the synthetic routes which you can look for. Another term that you have to be familiar with is the retrosynthetic or antithetic analysis. What we mean by this term is Retrosynthetic or antithetic analysis is a problem resolving method for converting the structure of a synthetic target molecule to a sequence of gradually simpler structures through a path which eventually leads to simple or commercially available starting materials for a chemical synthesis. So, dear students, retrosynthesis, we have given you a initial idea in this particular module, and we will be taking different routes, different examples, and the more you practice you will become comfortable, and then you can look up at any target molecule and design your own retrosynthetic route via the disconnection approach and via the various conversions, the retrosynthetic approaches that we have talked about and we will be dealing in further. So, let us try to summarize what we have learned in this module. We have learned that organic molecules are diverse in nature and there are numerous applications in all fields of life. If we talk about these molecules getting synthesized in lab, then synthesis of the organic molecules is a challenging field. And how the organic synthetic chemists handle, they often use the retrosynthesis or the disconnection approach. So, the synthesis requires the help of disconnection approach for the target molecule, and then you look up at the various possible routes by the various options. The backward way of observing a reaction is known as retrosynthetic analysis. Retrosynthetic or antithetic analysis, if we look for a proper definition, is a problem resolving method for converting the structure of a synthetic target molecule to a sequence of gradually simpler structures through a path which eventually leads to simple or commercially available starting materials for the chemical synthesis of that particular target molecule. And most of the times it is not only one route, but we have many routes, but then out of these routes you have to look up at overall commercially viable route, and that can be chosen for mass scale production of these compounds. Through the disconnection method we also studied, we actually break the entire molecule into smaller molecule starting materials on first of all paper, then join them by the various chemical reaction. So, this particular topic of study, that is the retrosynthesis, will require your knowledge of all the earlier organic chemistry and reactions. So, I suggest you should revise all the reactions, and while doing then also you can refer that okay, this is how the chloro can be converted into OH, or aldehyde can be oxidized to carboxylic acid, or carboxylic can be reduced to aldehyde, and so on. So, all the various conversions will be very useful when you are dealing with the retrosynthesis. And the toughest job in planning a retrosynthetic analysis is recognizing where to make the disconnections. So, that is very important that you have to keep in mind. And another thing I will like to summarize with you is that the various important transformations in retrosynthesis which will be handy and useful to you. One is functional group interconversion, where one functional group is interconverted into other, and for that all the reaction, the functional group chemistry that you have studied will be very much handy. Another thing is you can do the functional group addition, that is maintaining the same functional group, you add another functional group. Obviously, that also will require multi-step conversion, always it need not be a single step. Another strategy is the functional group removal, that is if you are already having 2 or 3 groups, one of them is removed and then you are getting this conversion happening. You can even do the functional group transposition, which is you can call it as starting from one particular compound, it is only the change in position and of the functional groups. In other words, you are getting the isomer of what you are starting with to reach to where the target molecule you want to synthesize or design. So, with this beginning, I am very sure that this module has given you the idea about the disconnection, the retrosynthetic approach, and from next and subsequent modules we will be going into more in depth study of this particular topic.